And these experiments are usually done with different substrate concentrations. So we usually leave the enzyme concentration constant. We have different substrate concentrations, usually measured in concentration, millimolar, for example. 0, 1, 2, 5, etc. And we measure how fast this enzyme actually uses the substrate and produces a product. So usually we measure it as rate. So that could be millimolar per minute or so. And we measure some numbers here. And then I showed you already last time what it looks like. When we plot these data, we would plot the substrate concentration on the x-axis, and we plot the speed of the reaction on the y-axis. Excel can do that for you, so it's pretty straightforward. And what we would get is something like that. This bent graph. Now, what does this graph actually tell us? Well, first of all, we notice that there is this plateau here. Yeah? What does this plateau indicate? Well, it indicates that we can throw more and more substrate in, and it doesn't matter because it still stays the same. This is actually the maximum velocity. This is Vmax. So we can go round here and say this would be our Vmax. Hey, cool! We found our first enzyme parameter. Because Vmax tells us how the enzyme behaves at very high substrate concentrations. We got enzyme parameter, Vmax. How cool is that? We could, in theory, measure Vmax over Km. And we said this is at very, very low substrate concentrations. And we can think of it basically as the gradient here. This is the gradient here, Vmax over Km. Not terribly easy to measure in this, but in principle we could do it. Hey, we've got our second enzyme parameter. So, what else do we have to find? What's missing? What's the third one? Loud? Km. Km. How on earth are we going to find Km? What did we say about Km? What do we know about Km? We said Km is actually the substrate concentration that gives us half of Vmax. Yeah? So all I need to do is I need to say, okay, let's take half of Vmax. Now I know this one here, this guy here, is my Vmax. It gives me a certain reading. So I just simply take half of Vmax. That might be, let's change the color, that might be around here. So this point here is half of Vmax. This blue one. And now I need to find out what is the substrate concentration that gives me half of Vmax. So all I need to do is I actually move over and down. Okay? And this substrate concentration here, this is the substrate concentration that gives me half of Vmax, and that is identical to Km. So, in principle, I have my three enzyme parameters. I have Vmax. From Vmax, I can very easily find half of Vmax. From half of Vmax, I simply go over to where the line is, go down vertically, and get my Km. This is this substrate concentration. And this substrate concentration, this Km, tells me how much the enzyme actually likes the substrate. Supermodel or dead ugly? Yeah? Got that? It's pretty easy, isn't it? Pretty straightforward. Well, this thing, actually, I think I introduced that to you. This is called a Michaelis-Menten plot. So in theory, we could use this Michaelis-Menten plot to find all three of our enzyme parameters. I say in theory, because this plot, this Michaelis-Menten plot, has a bit of an issue. It's a plot with an attitude, if you like. What's the problem with this guy? Now, I give you another Michaelis-Menten plot. V, substrate concentration. And we do our experiment and record for different substrates, for different substrate concentrations, I should say. We record the speed, how quickly the enzyme does something. And we find something like that. Unfortunately, we can't do any further experiments because the technician forgot to order the substrate and we are running out. We don't have any more substrate. This happens far more often than you think. This could be because the substrate is extremely expensive, or it could be that the substrate is insoluble and therefore we can't do any further experiments with it. Okay, we've got sort of a graph. Let's do the three enzyme parameters. Where is Vmax? Megan goes like that. It's either she's cold or she's trying to say there is no Vmax. Can't find a Vmax. It hasn't plateaued. So we could try and figure out what is our Vmax. So we could, in theory, go along and say, well, could be perhaps like that. Yeah? Looks quite nice, actually. And we would get a sort of a Vmax about here. Well, I might argue, well, doesn't look like it. We could go still like that. Yeah? So another Vmax would be up here. Or the whole thing just simply goes like that. So we would have a Vmax here. What a mess. We could get our Vmax over Km because that's the gradient, so we are pretty sure about that. But we can't get a good Vmax. Now, if we can't get a good Vmax, it's flippin' difficult to get a good half of Vmax. Well, we need the half of Vmax to get the Km, don't we? So where is our Km? Well, Km could be, well, here, could be here, could be here. Could be anything from here to here. So I think predicting the numbers in the national lottery would be more accurate than trying to get a Km. And Km tells us about the affinity. Bloody hell. And actually, this is the reason why you can't rely on a Michaelis-Menten plot. Let me put it this way. A Michaelis-Menten plot, unless you are specifically asked for that, a Michaelis-Menten plot is an absolute no, 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 no. You never use a Michaelis-Menten plot. A Michaelis-Menten plot is as safe as a condom with a hole in it. Yeah? Just simply forget it. Do not do it. And the reason for that is because we are dealing with a curved line. And a curved line we can't interpolate. We don't know where this curved line ends. Oh, damn. What are we going to do with this thing? How do we find our 3 parameters? Well, what we can do with this thing is, let's write down the Michaelis-Menten equation and let's see whether we can change that into something more palatable. Bless you. V equals Vmax times S over Km plus S. And if you like, I can write the left-hand side of the equation as V over 1. Anything divided by 1 is still whatever it is. And now I do something really, really dirty and filthy. I make this equation to do a handstand. How do I do that? Well, handstand on the left side, please. 1 over V. Handstand on the right-hand side, please. Km plus S divided by Vmax times S. So I made this equation to a handstand. So who cares? What have I gained with that? Well, I can write the right-hand side in a slightly different form. I can take it apart, and my sort of separation line is here. And I can write this as Km over Vmax times 1 over S. So this is this part here. Yeah? Plus S over Vmax times S. So I've just taken this fraction apart, and I've rewritten this bit here, this red bit here, a little bit. So, does that help us in any way? Maybe. Let's have a look. That is 1 over V. First of all, we can cancel out S on this at the back. So we have 1 over V equals Km over Vmax times 1 over S plus 1 over Vmax. You agree? Thank you. Bing! It was sort of, was that the penny dropped? Does that help us, the way I've written it? Let me show you what happens. Y equals mx plus c. Does that look familiar? Does that ring a bell? What is that? It's the equation of a straight line. Exactly. So, we have y, we have x. This here is our line. This part here, what would that be in the equation for a straight line? That's our c. And the gradient, what's that? That's m. Or in other words, for our enzyme, if we do it, let me do it here. What is our y-axis? Loud? 1 over v. Good. What is our x-axis? Loud? 1 over s. Good. What is this point here? One over Vmax. Excellent. What is the gradient? Yes, the gradient is Km over Vmax. So let me draw this nicely again. One over V, 1 over S, this point here, is 1 over Vmax. The gradient is Km over Vmax. And if we extend this graph into the negative range, something like that. Of course, we don't have a negative substrate concentration. It's just we extend the graph for mathematical reasons. We find that this point here is minus 1 over Km. And you can do that. You can try the maths out yourself. That's, or just believe me. So, what have we gained with this? We converted our horrible curve actually into a straight line. And a straight line we can very easily interpolate. We can do even more with a straight line. We can do a regression analysis. And you know what this is, because we've done it in stats. Yeah? With this R square, with this R. How good do the data actually fit? What about our enzyme parameters? Because that is what we set out to gain. Well, we didn't get the best deal, but we got a reasonable deal. Instead of Vmax, we got 1 over Vmax. As soon as I have 1 over Vmax, I simply put that into the calculator, and I can calculate it to give me Vmax. I just have to do 1 over the number that I get for 1 over Vmax. Yeah? I haven't got Vmax over Km, but I've got Km over Vmax, the other way around. So I just take the inverse of this number here, and I get my Vmax over Km. I didn't get Km, but I got my minus 1 over Km. Next best, because I just simply take the value that I get for 1 over Km and inverse that, and I get my Km. So instead of dealing with this horrible Michaelis-Menten graph, I use this particular graph, and I get my enzyme, sort of my enzyme parameters. I still have to do a little bit of stuff with it. I have to inverse all the numbers that I get, but then I get it. This graph, and biochemists absolutely love this graph. It is called a Lineweaver-Burk plot, or because you take V and substrate concentration, you make them do a handstand, basically. It's also called a double reciprocal plot. And this Lineweaver and Burk, they basically use the Michaelis-Menten equation exactly as I showed you, and transformed that mathematically. What we have done is just simple maths. Just do the handstand thing. And I could convert this horrible curvy line into a straight line, which makes the analysis of enzymes much easier. Does that make sense? Yeah? Okay, so what you should have gained from today is, when I show you a Lineweaver-Burk plot, you should be able to tell me what are the different points on it. And obviously we will do some exercises to that. I also want you to remember what these three enzyme parameters stand for. Vmax, how the enzyme behaves at high substrate. Vmax over Km, how the enzyme behaves at low substrate. And Km tells us about the affinity. High Km, low. Low Km, high affinity. On Monday, please bring along some graph paper, because I will show you why you should not use a Lineweaver-Burk plot. See you on Friday.